Today's lecture will focus on the real-time polymerase chain reaction. This module will focus on the fundamentals. PCR reaction, which is designated as RT-PCR, qRT-PCR, or RT-qPCR, is assumed significance in the modern molecular biology laboratory as a result of its attributes, which include sensitivity, specificity, reproducibility, and the capability to detect trace amounts of DNA which cannot be detected using conventional PCR. Real-time PCR monitors the fluorescence emitted during the reaction as an indicator of amplicon production at the end of each PCR cycle in real time, as opposed to the conventional endpoint detection. In the case of PCR, the thermal cycler consists of a conventional thermal cycler, which is conjugated with a light source and an optical detection system. The real-time PCR is kinetic. It detects amplification associated with fluorescence at the end of each cycle of PCR. No gel-based analysis is required at the end of PCR. And computer-based analysis of the cycle fluorescence gives an accurate detection of the copy number of the DNA molecules. Advantages of qRT-PCR are many. It is not influenced by non-specific amplification. The cycling time is shorter. It has a wider dynamic range. It requires very low starting concentrations of DNA or RNA to the order of 3 picograms. The specificity of amplification can be confirmed. Post-PCR processing of samples is eliminated. In order to carry out a RT-PCR protocol, DNA can be incorporated directly into the qRT-PCR system. However, RNA must be converted into its complementary DNA or cDNA in order for the qRT-PCR to be successful. One of the most commonly used fluorophores in RT-PCR is the SYBR green dye. SYBR green absorbs blue light at a wavelength of 488 nanometers and emits green light at a wavelength of 522 nanometers. This absorbed wavelength is provided by the optical system, and the emitted fluorescence is detected using a fluorescent detector array. The SYBR green binds specifically to double-stranded DNA. It does not bind to single-stranded DNA. This renders it visible during the process of extension and annealing. In the case of SYBR green, during the denaturation step, the SYBR green molecules remain in solution. During the annealing step, the SYBR green molecules will commence binding to the DNA molecule. And during the extension step, during which the DNA is double-stranded, the signal intensity will be maximized due to the binding of the SYBR green molecules to the double-stranded DNA. DNA binding dye SYBR green binds stoichiometrically to the double-stranded DNA and not to single-stranded DNA. During the first 5 to 15 cycles of the polymerase chain reaction amplification cycle, there is a low copy number of SYBR green molecules and there is a low fluorescence signal. However, after the 15th cycle, the copy number of the PCR amplicons increases with a corresponding increase in the fluorescence signal. This is termed as the CT value or the threshold value. As you can see in this graph, the threshold value is determined by the number of DNA molecules in the original analyte sample. For instance, when we have low concentrations of DNA, the CT value will move towards the right-hand side, and when the concentration of DNA in the analyte is higher, the CT value moves towards the left-hand side of this graph. The threshold value or the CT value is the cycle at which a significant increase in the delta Rn or the relative fluorescence is first detected. This parameter is used for quantification. If there is no amplification beyond a CT value of 40, it means that the sample does not contain DNA. This is an example of the graph indicating two CT values of 20 and 28. The sample B has a lower concentration of DNA as is indicated by the red line. Sample A has a higher concentration of DNA as is indicated in the blue line. This is an example of the terms used for calculation of the delta Rn. There is a baseline at which no fluorescence is detected and a threshold value beyond which the fluorescence is detected. Efficiency is calculated using the formula which is stated in this slide. The efficiency of PCR should be 90 to 100% with an ideal slope of negative 3.3. PCR can be validated by testing the primers in association with their respective target. The primer pair that is chosen should have the highest delta Rn and a lower CT value. In case the DNA template is too concentrated, the researcher may require to dilute the DNA sample. One of the ways in which non-specific amplification can be detected is the melt curve analysis. Subsequent to the qRT-PCR process, the sample can be subjected to melt curve analysis. An indication of improper PCR amplification or non-target amplification is the presence of two peaks in the graph. SYBR has specific advantages and disadvantages. It can bind to non-specific targets, and this requires extensive optimization. However, overall, SYBR is ideal for the detection of specific targets in DNA molecules. SYBR should not be used during allelic discrimination assays. It should not be multiplexed with multiple primer pairs and for the amplification of rare transcripts. It can also be applied to detect viruses in DNA samples. However, for diagnostic purposes, it should not be utilized to declare or detect low levels of pathogens. Your module on RT-PCR fundamentals. Thank you.